Hello students, the chapter rotation is now almost complete except for the topics mechanical energy associated with rotation and angular momentum and its conservation laws. So let's get started. Rotational kinetic energy. Let us first consider a rigid body. Let that be in rotation. Already we know translation kinetic energy, that is equal to half mv square. So if this body, rigid body I have considered here, which is in rotation, let's consider these axes as x and y axis. Now I am pointing to a mass which is a constituent mass mi and it has some velocity vi. Now its location with respect to center is given by r, which is at angular position theta with respect to the x-axis. Let us take origin as O. Now if we have to write kinetic energy of this particular particle, which is constituent particle of the rigid body, then we can write Ki to be equal to half mi vi square. Let this be the equation number 1. Now since every particle in this rigid body should be having the same angular speed, so we can write Vi as omega Ri, and then we can write total kinetic energy of all the particles to be equal to, it should be summation of Ki. So let us write the summation term, that will be half mi vi square. And it can be written as half mi, omega is constant for all the particles, so it should be omega square Ri square. Now omega, as it is constant, so can be taken outside the summation, and half omega square if taken outside, this term will be summation of mi Ri square. What is this term, summation of mi Ri square? Does this seem familiar to you? Of course, you know this very well. This is known as moment of inertia. So from here we got moment of inertia of a rotating body to be equal to half I omega square, which is the rotational kinetic energy. Again you can see it is simply an analog term for kinetic energy in translation, because mass has been replaced by I and V has been replaced by omega. So this is the term associated with rotational kinetic energy. Now as you know, all the laws are same as in translation, so here also we can write work energy theorem, but this time it has to be rotational work. And you know what is rotational work? This time it should be work done in rotation, that should be equal to, already we have derived this, so it has to be tau dot d theta. And since work energy theorem can be written for translational motion as work done should be equal to change in kinetic energy. So here the same we can write for rotation as well, that net work done should be equal to change in kinetic energy, and this time the kinetic energy is rotational kinetic energy. So again we got a similar term in rotation that we used to write for translation. The next thing is conservation of mechanical energy. What is conservation of mechanical energy for translation? I had explained that no external work is being done on the system. Mechanical energy of the system has to be conserved. Here also it is the same thing. So we can write again delta K, delta U has to be equal to 0 if work done by external torque is 0. The only thing is that this time we have to consider work done due to torque and not the force. So we can apply conservation of mechanical energy also for rotation where no work is done by the external torque. The next is power. As we know, it is work, energy and power. So next I am coming to the term power. How is it defined? Already we have derived power developed by a torque. So it should be d by dt of work done, that is tau dot theta, that will be tau dot omega. So these are all work, energy and power for the rotational motion. Let us consider first one example based on these concepts. A uniform cylinder of mass m and radius r, radius is given r, mass is given m, initially at rest is mounted so as to rotate freely about a horizontal axis that passes through the central axis of the cylinder. So, the cylinder is fixed at this point about its center. A constant force F acts on the cylinder as shown here. Calculate angular velocity of cylinder as it rotates by an angle of pi, that is the half revolution. So let us see how this can be solved. If I write work done by the constant force F, because it is a constant force, its torque also is constant, so directly we can write work done to be equal to torque into delta theta. No need to integrate here, this is a constant torque. And what is torque by this force? It has to be F into R multiplied with delta theta, which is given pi here. Now, is there any other torque also? No, no other torque will be there because weight will act on the center of mass and normal reaction by peg also has to be at the center of mass. So, there will be no other torque than torque of this force F. I have written work done by this force F, and as we can write the work energy theorem, so this work done should be equal to change in kinetic energy. This time it is a pure rotation, so kinetic energy should be written as half I, it should be omega final square minus omega initial square, which is final kinetic energy minus initial kinetic energy. But since the cylinder was at rest, so this omega I has to be 0, and directly we can write Fr pi to be equal to 1 by 2 I. We can substitute the value for cylinder, that has to be equal to mr square by 2. So it will be mr square by 2 omega square, which is the final angular velocity. From here we got omega to be equal to root under 4 f pi upon mr. This is angular velocity of the cylinder as it rotates by an angle theta. One more question I have related to energy. A uniform circular disc has radius r and mass m. A particle also of mass m fixed at a point A on the wedge of the disc as in figure. The disc can rotate freely about a fixed horizontal chord PQ, that is at a distance r by 4 from the center of the disc. This condition is shown here in the diagram. The line AC is perpendicular to PQ and initially the disc is held vertical. A is at the highest point. From here, now it is allowed to fall so that it starts rotating about PQ. We have to find linear speed of particle as it reaches its lowest position. Okay, let us start solving this. First, write the total initial mechanical energy for the system. What it should be? I am writing mechanical energy initial. It will be mg r by 4, that is for the disc, plus mg 5 by 4 r. Here I have taken reference as PQ. So if potential energy at PQ is 0, all the heights are written with respect to PQ. This is initial mechanical energy as the system is at rest initially. So only gravitational potential energy I have written here. Now when the particle A reaches the lowest position, what will be the mechanical energy then? Mechanical energy final, if I write, it should be equal to, because now the center as well as A has come down by the same height with respect to PQ. Now A has reached the lowermost position. So it will be equal to, if you calculate, this will be 3 by 2 mgr. If you solve the first one, that will be 3 by 2 mgr. So the next one, as the whole height has been come below the line PQ, the same quantity we will get for gravitational potential energy but with negative sign. So it is minus 3 by 2 mgr. But this time we have to write kinetic energy as well. So let us first write kinetic energy for the system, and which is the final kinetic energy. First calculate moment of inertia. Once we know moment of inertia, directly we can write half I omega square. So let us first calculate this. I can be written as, for the disk it should be mr square by 4 about the diameter, and then I am applying parallel axis theorem. So it should be m and square of r by 4. This is moment of inertia for the disk. And what about the particle A? That has to be equal to m, and its distance is 5r by 4. So this should be square of 5r by 4. This is moment of inertia of the whole body about PQ, and its value will come out to be equal to 30 by 16 mr square. So now I can directly substitute this value of I in expression for kinetic energy. This will be minus 3 by 2 mgr, plus we have to write half I omega square. So it will be half, in place of I we have to write 30 by 16 mr square omega square. On solving it further, it will be 1 by 2 30 by 16 mr square omega square to be equal to 3 mgr. Now on solving, omega will come out to be 4 under root g by 5r. This is the angular velocity of the whole system. Now what about linear velocity of particle? So we have to write for linear velocity of particle A when it has reached the lowermost point, VA can be written as you know, always linear velocity can be written as omega r for pure rotation, where r is distance of particle from the rotation axis. Here rotation axis is PQ. So from PQ if I write the distance of A, that has to be equal to 5r by 4. So this is 5r by 4 omega. Putting the values, it will be root under 5gr. This is the linear velocity of particle A when it has reached its lowest position. One small subtopic is remaining, that is angular momentum. So let us see what is this term. You are already familiar with the term linear momentum. So here let us consider this angular momentum, how it is different from linear momentum. Now as you know, linear momentum P we denote generally by, that is mv. This is the linear momentum. Angular momentum, by just taking analog of linear momentum, we can say that angular momentum can be defined as, it should be moment of linear momentum, because as we know that torque is moment of force. So we can define angular momentum also as torque of linear momentum. As we know that what is relation between force and torque, we can write the same relation for linear momentum and angular momentum, because force is defined as rate of change of linear momentum and torque is defined as rate of change of angular momentum. So by simply taking the analog, we can say that L should be equal to, L is the notation used for angular momentum. It can be written as R cross P, that is cross product of position vector with respect to rotation axis and the momentum. First I am writing this for a particle, and then we'll extend the concept for an extended body as well. So let us consider a particle which is having mass m, velocity v. Its position with respect to origin is given as r. So we can write L to be equal to r cross p. Its magnitude can be written as rp sine theta, where theta is angle between r and p. Now angular momentum will be 0 if either p becomes 0, p vanishes, or the r vanishes when the particle is at origin, or if angle between r and p is either 0 or 180 degree. So these are the conditions when angular velocity will become 0. Now to get the term torque, we can write dl by dt, because this is definition of torque. Torque can be defined as rate of change of angular momentum. So if I differentiate angular momentum with respect to time, that will be d by dt of r cross p, and if I differentiate it, it will produce dr by dt cross p plus r cross dp by dt. Now we know that dr by dt can be written as velocity, so this term will be v cross p. What is p? P is also mv, so this will be 0. Plus, because v and p has to be in same direction, so its cross product has to be 0. Plus r cross dp by dt. What is dp by dt? That is force. And from here we got dl by dt to be equal to torque. And now we can say time rate of change of angular momentum of a particle is equal to torque. This is the rotational analog of equation F is equal to dp by dt. In translation, we were using F is equal to dp by dt, and here we got torque is equal to dl by dt. So linear momentum is having an analog term in rotation, that is angular momentum. Now this all I have discussed for a single particle, but what if an extended body is there? Then you have to write, because for extended body we have to simply summarize the term for all the constituent particles. So we can write L to be equal to, it has to be summation of Ri cross Pi, and we can write dl by dt to be equal to, of course it has to be summation of all the torques. In this way we can write angular momentum for the extended body, that will be equal to summation of angular momentum of all the constituent particles. Again, by seeing the analog, we can write L as I omega as well, because if linear momentum can be written as m multiplied with v, so if I replace m with I and v with omega, we can write the angular momentum that has to be equal to I omega. So this is one more definition which we can use for an extended body. Of course, for a single particle it has to be r cross mv, and for extended body either we can write in summation form or directly can use I omega. This is all about mathematical definition of angular momentum. Now let us see its conservation law. So what is conservation of angular momentum? As we write, for linear momentum conservation, whenever external force is 0, we can write linear momentum to be conserved. So here also we can write that if external torque is 0, then L should be constant, which is known as conservation of angular momentum, and then we can write L initial to be L final. This is, though appears very small thing, but it is very important from numerical point of view, because in a number of numericals you have to write this concept as we had used for linear momentum conservation. Now for rotation, if we see that no external torque is acting on the system, we can always write angular momentum initially to be equal to final angular momentum. This will provide one more equation, and that will solve in solving the given situation. Now with this concept we can write for an extended body that for the whole system, see this is a conservation law, so it cannot be written for a single particle or a single body. Always it should be for a combined system, for the whole system. So if we write for the whole system, and for extended body it can be written as I omega I to be equal to If omega F. Do remember, this is for the whole system, not for a single body. Now what if axis of rotation is not fixed? One situation, sometimes this kind of situation may arise when, let us consider a body which is rotating with omega. This is RCM, position vector with respect to origin, and VCM is moving as well. So here the body is rotating about center of mass, and then center of mass also is moving. So if we have to write angular momentum of a rigid body, if axis of rotation is not fixed, in this case we can write angular momentum of particle as angular momentum of particle with respect to O plus angular momentum of center of mass. And what this term will be? It has to be m RCM cross VCM plus ICM omega. Here we have considered that this particle is rotating about center of mass, and then center of mass is translating. So we have to consider both the parts. First, it has to be for center of mass, which is translating, and then rotation about center of mass. So on writing these two terms, then we can write angular momentum for the whole body when axis of rotation is not fixed. Let us solve one example. A horizontal 90 kg merry-go-round is a solid disc of radius 1.5 meter and is started from rest by a constant horizontal force of 50 Newton applied tangentially to the edge of the disc. The kinetic energy of the disc after 3 seconds is. If we write the torque equation for this system, then it will be net torque to be equal to I alpha. So from here we can write alpha is net torque upon I. And on substituting the value as F is the external force, which is the horizontal force, so its torque will be Fr divided by I we have to write for disc, so its value will be mr square by 2. That is 2 Fr upon mr square. 1 r also got cancelled. It will be only 2F upon mr. And from definition of rotational kinetic energy and the rigid body under constant angular acceleration, we can write K to be equal to half I omega square, which will be 1 by 2 I. Omega here is not constant, it is moving with constant acceleration, so omega can be written as initial omega plus alpha t, because angular acceleration is provided here, and square of this value. On substituting now, we will get 1 by 2 I alpha square t square. Initially it was at rest, so omega I has to be equal to 0. On substituting all the numerical values, this will come out to be equal to, first its value will be F square t square upon m, and then finally 250 joule, which is our option number C. Let us consider one numerical based on this concept. Just now we have learned a cylinder of mass 5 kg and radius 10 cm is moving on a horizontal surface with speed 5 meter per second and angular speed about axis through center of mass, that is 10 radian per second. Find the angular momentum of cylinder about point of contact. Let us consider this cylinder which is rolling on the contact surface. Now its center is moving with speed 5 meter per second and omega is 10 radian per second. We have to write angular momentum about point of contact, so that can be written as LO plus LCM, where LO is angular momentum of center of mass with respect to point of contact. Now if I write these two terms separately, LO can be written as MVCM and then R perpendicular with respect to point of contact. That will be equal to 5 into 5 into R perpendicular, as you can see, is equal to radius, which is 10 centimeter, so it has to be 1 by 10 meter. That will be 2.5 kg meter square per second, And what is the direction? As you can see here, it is clockwise. Next we have to write LCM. This is angular momentum with respect to center of mass. Now since it is in pure rotation, so directly it can be written as ICM multiplied with omega. That is half mr square into omega, and if I put all the values numerically, it will come out to be 1/4 kg meter square per second. And then the final result can be written about point of contact as LO plus LCM, that will be equal to 2.5 plus 0.25, that is equal to 2.75 kg meter square per second. With this, our chapter rotation is complete. I hope you learned all the concepts properly, and now we are going to solve few questions that have come in your competitive exams in previous years in our next session. Till then, keep practicing and enjoy studying. Goodbye.